Education, education, baby. Come on, education has no end. Education.
Giant covalent or atomic structures. It occurs in group 4 elements and some of their compounds. In this type of structure, we have atoms which are covalently bonded to other atoms infinitely throughout the structure. Consequently, this type of structure is very strong. So that is basically the introduction of giant covalent or giant atomic structures. They are normally found in group 4 elements and some of their compounds. We have atoms which are covalently bonded to each other throughout the structure, and therefore the structure is very strong. Now, substances with this type of structure are very hard solids, which are usually used as abrasives. Some examples of giant covalent structures are diamond, graphite, silicon 4 oxide. Yes, those are some examples of giant covalent structures. Now let's look at each one of them in details and see how they are formed. We start with diamond and graphite. These are the allotropes of carbon. Allotropes are different crystalline forms of the same element in the same physical state. So when we talk about diamond and graphite being allotropes of carbon, then we are talking about they are crystalline in nature and they are in the same physical state, that is in the solid state. Allotropy, on the other hand, is the existence of different crystalline forms of the same element in the same physical state. So there is a difference between allotropes and allotropy. One, allotropes are the crystalline forms in the same physical state, while allotropy is the existence of those crystalline forms in the same physical state. Now let's talk about diamond. In diamond, each carbon atom is covalently bonded to 4 other carbon atoms, forming a giant structure. Therefore, remember, carbon is in group 4. So the 4 outermost electrons in diamond are used in bonding. So each carbon atom is surrounded by 4 others, and this extends in all directions to form a very giant structure. In diamond, all the valency electrons are involved in bonding, leaving no free electrons. And that is why diamond does not conduct electricity, because it lacks delocalized electrons in its structure. All the electrons are used in bonding in diamond. Now let us look at the structure of diamond. So the diagram alongside shows the structure of diamond. You can see all carbon atoms are surrounded by other carbon atoms. No free electrons are left in the bonding of diamond. So that is how the structure extends to all directions, forming a giant structure which is very hard. Properties of diamond. Number 1, it is colorless, it is transparent, and it is shiny, crystalline substance. Colorless, transparent, and shiny crystalline substance. It has a high density of about 3.51 grams per centimeters cubed. This is due to the close packing of the carbon atoms. It is the hardest substance due to uniformity of the strong covalent bonds throughout the structure. It has a high melting and boiling point due to strong covalent bonds. So the melting and boiling points of diamond are very high as a result of the strong covalent bonds within the structure. Uses of diamond. It is used for drilling and cutting other metals due to its hardness. So it is such an hard substance that it can be used for drilling and cutting of other metals. It is also used in making ornaments, jewelry, because it is shiny when polished. So those are the two uses of diamond: drilling metals and cutting other metals, and making ornaments or jewelry. Let us now move on to graphite. In graphite, each carbon atom is covalently bonded to 3 other carbon atoms, leaving 1 electron free. Hence, graphite conducts heat and electricity due to presence of that delocalized electron. So the delocalized electrons in each carbon can move within the structure, and that's why we call them delocalized. So the ability to move within the structure is what enables graphite to conduct electricity. Graphite is made up of hexagonal layers which can easily slide over each other, and that is why it is used as a lubricant. So that is one use of graphite. The ability of the hexagonal layers to slide over each other makes it useful as a lubricant. The hexagonal layers are held together by weak van der Waals forces, and that is why graphite is soft with a lower boiling point than diamond. Reasons graphite is used as an electrode during electrolysis are: it is cheap, it is a good conductor, it is inactive. So electrolysis is the process by which an electrolyte is decomposed by passing an electric current through it. So we prefer the use of graphite as the electrodes, and these are the 3 reasons. 1, graphite is cheap, it is a good conductor, and it is inert. Does not react with most chemicals. Therefore, it is useful in electrolysis. The structure of graphite. So this is the structure of graphite. You can see it is composed of hexagonal layers which are over each other, about 0.35 nanometers far apart. They are joined together by weak van der Waals forces, and the carbon atoms themselves are combined using a covalent bond. So you can notice that a carbon atom is only surrounded by 3 bonds. So the 4th electron is not used in bonding. Instead, it is the one we are saying it is delocalized within the structure, and that is why graphite is a good conductor of electricity. Uses of graphite. One of them is that it's used as an electrode in electrolysis because it's a good conductor of electricity. It is also used to make pencil leads because the hexagonal layers are held together by weak van der Waals forces, hence they can easily peel off. It is used as a lubricant due to hexagonal layers held together by weak van der Waals forces, which can easily slide over each other when pressed. Now let's look at another compound which has the giant atomic structure, and that is silicon 4 oxide. Now in silicon 4 oxide, each silicon atom is covalently bonded to 4 oxygen atoms, and each oxygen atom is covalently bonded to 2 silicon atoms. This results to a giant covalent structure with very strong covalent bonds. Now the diagram shown is a diagram of the structure of silicon 4 oxide. You can see the oxygen atoms and the silicon atoms surrounding each other, forming a giant atomic or covalent structure. Silicon is another structure which is giant atomic. It is in group 4, period 3, and has a giant atomic structure whereby each silicon is covalently bonded to 4 other silicon atoms, forming a giant covalent structure with very strong covalent bonds. So the structure of silicon is as shown. We have the silicon atoms joining each other to form a very big structure which is giant atomic. Now, properties of giant covalent structures. Generally, they have high melting and boiling points due to the strong covalent bonds. Another property is that they are poor conductors of heat and electricity, except graphite. Silicon is a semiconductor. And the last one is that they are insoluble in water. They are insoluble in water.
Our education, baby. Come on.